Okay, folks, like I said, I never promised you a rose garden, okay? That last video was like super long. It sets a record by far for any video I've ever made. And I could have broken it up into smaller parts, but then I would have broken up that first problem. Took a lot of explanation. I know, I'm babbling on here again, making this video longer. But please look over that video. Go through it part by part if you have to. Make sure you understand it. If you're taking the test, the next time that we're together, yeah, and you're going through that video to try to figure out that problem, you're not going to have time. So you do have to go through it, dissect it, and as many times as it takes for you to be successful. All right, you will have a problem like that. It'll be worth a lot of points, so you don't want to lose those points. So please get it before you do the test. All right, let's go. Let's go. This video, this will be shorter, much shorter. I promise. I'll do it.
Well, not the way you're babbling.
Yeah, angsty Billy. Jeez, relax. Okay, let's check out problem number 2. Problem number 2 says consider the reaction A goes to B. Okay, right there. Consider the reaction A goes to B. Now, the rate of the reaction is given, so you're given the rate. When the concentration of A is, and you're given the concentration of one of the chemicals, calculate the rate constant. Okay. A, for a first order reaction. What's that? The first order! Today is the day, the rise of the first order! Yeah! Star Wars, anybody? Anybody? First order? They were the bad guys, okay? Bad guys. Yeah, first. Okay. First order. Besides Star Wars, what does it mean? Well, let's go back to the last problem. No! Relax. Last problem, rate law. Just look at it for a second, okay? So here is the rate law from, sorry, the last problem. Okay, that was it from the last problem, remember? Okay, so what do we have? This concentration is squared. This concentration was to the first power. Now, we didn't write it. You can. It's kind of like writing H2O1. It's not wrong, you just don't do it. And it's technically correct, but people will laugh at you behind your back. When you walk away from the water cooler, people are going to be laughing at you. Yeah, you see what they did? They put a 1. Yeah, what a noob. All right, well, but you can. So we don't put it here. It's understood to be there. This is a third order reaction. Third order reaction, yes, count the superscripts. Count up the exponents. Count the exponents up, add them. That's the order of the reaction. 2, 1, this is a third order reaction. First and second order reactions are the easier ones, and those are the ones we're going to be sticking with in our class, but there are more difficult reactions, and the chemistry and the equations used get more involved as you get a higher and higher order. This would be a third order reaction. So just add up the exponents. If they are both 1s, or in other words, if it looked like this, that would be a second order reaction. Okay? Or what if we had a reaction where that was a 1 and this was a 0? A 0? You can't have a 0. Yeah, you can. That would just mean that, for example, the hydrogen has no effect on the rate. So you could put as much hydrogen in the reaction as you want, it just doesn't have any effect on the rate. Sometimes things don't have an effect on a rate and they get an exponent of 0. So this would be a first order reaction, 1 plus 0, 1. All right, so this problem is saying that we have a first order reaction, and it gives me the A to B. So I look at this. A goes to B. And let's write our rate law. Oh, we have to go through all this stuff to get all the data. No, relax. I'm told already it's a first order reaction. The reason you have to go through the data, like in the last problem, is to determine what the exponents are. This is telling me. That's not telling me. Yeah, it is. It is. Check it out. Remember rate laws? They're written for the reactants only. So the rate of this reaction is going to be equal to K. You got to have a K value, a constant value. And you're going to put in brackets the concentration of your reactants. In this case, reactant. I only have one thing. I have this thing transforming into this. So Transformers, robots in disguise. So this is transforming into that. So that's my only reactant, so that goes here. And it told me it's a first order reaction. So there's a 1 here. Of course, I'm not going to write it. You can if you want to. But there's a 1 there. So therefore, that's the rate law. That's it. I've got one reactant. It told me it's first order, so I don't have to dig through the data to figure it out. That's a 1. There's my reaction. That's it. That's the 1. Okay, so what did it want? Was that what it wanted? Does it want the rate law? Let's see. Okay, calculate the rate constant. Okay, so we want the constant. So we want this. So K is going to be equal to rate divided by A. The concentration of A. There's my setup to solve for part A. This is going to be much, much quicker than that last problem. That was a doozy. Okay, what do we got? I need the rate. Was I given that? I was given that. Nice. The rate of the reaction is 1.6 times 10 to the negative 2. So 1.6 times 10 to the negative 2 is 0.016. Times 10 to the negative 2. 1.6 times 10 to the negative 2. Okay, yep, 1, 2, go, got it. Okay, nailed it. All right, then the concentration of A. I was told the concentration of A is 0.35. Just going to put 0.35 down here. That's it. I will get the K value for this. Sweet. This is too easy. It's too easy. Sometimes problems you start with are harder than the problems down the line. That happens sometimes. So this isn't, you can do this. You can do this. Even angsty Billy can do this. Divide by 0.35, and we get 0.0457. I'll make that 0.046. 0.046. So this is the rate constant, the constant value that would go into this equation. And the units are always weird. Remember I told you in the last video? What you would do in this case is you would look at this. This would be, the concentration is in molar per second. All right. And your rate is in, you check this out, your rate is going to be right here. Your rate is in molar per second. Okay. I'm sorry, the rate's in molar per second. This isn't in molar. So molar per second rate over concentration in molar. So if I were to divide these, same thing as flipping and multiplying by the reciprocal, the m's cancel. I'm just showing you what the unit would be for this, and it won't be the same for the next one. That's my point. My point is I'm going to show you that the units are different. So you're going to end up with, for the unit for this, is just S is on the bottom, so it's 1 over S. It's a weird unit, right? It's just weird. Okay, but just going to show you. Again, I don't care that you get the units correct. I just care you get the number correct. You get the number, happy camper. Okay, get the number. Let's try B. B says, well, what would happen to the rate constant if this were a second order? So A is a second order. That means a second order for A would have a 2 for an exponent. Second order, because it's got a 2, and that's the only reactant, so 2 plus nothing else is 2. So if it's second order, that's squared. So this is squared, and that's going to change. So do the math. All right, doing the math. 0.35 times 0.35, let's put that in the back pocket, 0.1125 on the bottom, 0.1225, and then 0.016 divided by 0.1225, enter 0.131. We round it to 2 significant figures. These have 2, that is 2, so 0.13. I'm not too picky about significant figures as long as you don't give me the calculator answer. We're not in analytical chemistry class. In that case, you would. And some professors are. Some are like, no matter what kind of chemistry, what level of chemistry, we've got to watch those significant figures. Okay, let's just be aware of them. That don't give me the long calculator answer. We're good. If you put 0.13 or 0.131, fine. What about the units this time? Okay, rate was m over seconds. This was m. But now we're squaring it, so there are 2 of them. And take that, multiply by the reciprocal. One of the m's would end up canceling, and I'd be left with an m on the bottom. Okay, so the unit here would be m times s, or ms, or sm. It doesn't make any difference which way you do it. Okay, different than the one before. See, the units always change with these rate constants depending on the problem. So again, don't worry about that. Just make sure you can get the number. If you can get that, then we are good to go. We are good to go. And these equations that we're going to be using coming up, I was just going to say equation we use. This equation that we're using for rate has to be determined by experimental data, or if you were told what the order is, that makes it easy. You can just go ahead and set the rate equation up depending on the order you were told. I will give you a problem like that last one. Now, yes, worth a lot of points. 30 minutes of video, make sure you know it, because you will not be able to watch 30 minutes of video doing the test. And I will give you one like this. Yes. Okay. Okay. So that is problem 2. I promise to keep this video a lot shorter. Should we, it's only 11 minutes. Should we end it? Let's take a look at the next problem. I will. I'll stop this video now because I know the next problem will probably take about the same amount of time, and I don't want to make it a long video again. So this video is done.